All right, let's talk about light. We all know it's famous for being the absolute fastest thing in the universe. Out in the vacuum of space, it's this unyielding force traveling in perfectly straight lines at mind-boggling speeds. I mean, it seems almost untouchable, right? But what if I told you that by simply putting different transparent materials in its way, we can force this cosmic speedster to slow down and bend completely to our will? In our explainer today, we're going to dive into the fascinating physics of exactly how and why light bends, and look at the incredible tools we use to manipulate it.
Okay, so here is our game plan for this explainer. We'll start by breaking down the actual process of refraction. Then we'll introduce spherical lenses, map out the rules for ray diagrams, explore how images are formed, and finally, we'll wrap up by tackling lens formulas and power. Let's get into it.
Part 1. The process of refraction, or how we actually bend light's path.
Now, what's really interesting here is how the sheer physical density of a material dictates exactly which way our light ray is going to bend. When light travels through one medium and then abruptly enters another, its speed actually changes, which causes its direction to shift. If light enters a rare medium, like air, where the particles are spread pretty far apart, the ray bends away from the imaginary perpendicular line that we call the normal. But if that same light plunges into a denser medium, say a solid block of glass or a pool of water where the particles are packed tightly together, it slows down and bends sharply toward that normal line.
But nature isn't just wildly bending this light wherever it feels like it. There are two absolute, unbreakable laws of refraction it has to obey. First off, the incident ray coming in, the refracted ray bending through the medium, and that imaginary perpendicular normal line, they all exist perfectly flat in the exact same plane. You're never going to see a ray suddenly jump out at you in 3D space. Second, there is a fixed mathematical relationship. If you take the sine of the angle of incidence and divide it by the sine of the angle of refraction, that resulting ratio is always constant for those two specific materials. It literally never wavers.
And that brings us to a massively foundational concept, the refractive index, which we represent with the lowercase letter n. You know that constant mathematical ratio we literally just talked about? Well, that is the refractive index. It's the precise measurement of a specific medium's ability to bend light. Actually, fun fact, it's the exact reason a diamond sparkles so much more than a standard piece of glass. A higher refractive index just means the material slows the light down more, which bends it more severely. It's absolutely crucial because it's the baseline number we need to understand how any two materials will interact optically.
Moving on to Part 2. Introduction to spherical lenses. The physical tools that bend light.
So, when you take two spherical or plane refracting surfaces and join them together, you create a transparent tool that we know as a lens. And there are two main types you really need to be familiar with. First, we have the convex lens. It bulges outward right in the middle, and its fundamental job is to converge incoming light rays. It brings them all together to a specific focal point. It's super versatile, capable of forming both real and virtual images. Then on the flip side, we have the concave lens. It caves inward, and it does the exact opposite. It diverges light rays, spreading them apart. Because of that spreading effect, a concave lens will always form a virtual diminished image. But before we start mapping out exactly how light travels through these lenses, we have to identify a critical safe zone. Right in the very center of the lens, sitting directly on the principal axis, lies the optical center, marked as O. Think of this point as a physics loophole. Any incident ray of light that passes directly through this optical center is going to go straight through the lens completely undeviated. It doesn't bend at all. It just keeps marching forward on its exact original path.
All right, Part 3. Rules for ray diagrams. Let's look at the geometry of light.
Let's move to and see how this builds, because to engineer optical devices, we need blueprints. Light follows 3 strict, super reliable geometric rules when passing through a lens. Ready? 1. A ray coming in parallel to the principal axis always passes through the focus. 2. The exact reverse. A ray passing through the focus first will exit completely parallel. And 3. Just like we saw a second ago, a ray hitting the optical center continues completely undeviated. Those are the only laws our light ray can follow.
Part 4. Image formation in lenses, predicting the projection.
And this brilliantly illustrates our ultimate cheat sheet for a convex lens. Instead of trying to memorize every single scenario, just look at the overall pattern. As the object moves closer to the lens from infinity, step by step toward the glass, the resulting image physically shifts and grows. Way out at infinity, it's just a tiny inverted speck. Move it closer, and the image perfectly mirrors it in size. But the true magic happens when you move the object incredibly close, right between the optical center and the focus. The image suddenly flips to the same side as the object, becoming virtual, upright, and highly enlarged. By the way, that exact scenario, that is the science behind how a magnifying glass works.
Now, after all those moving parts and complex scenarios for the convex lens, you're going to be pretty happy to know that concave lenses are much less complicated. Honestly, they are remarkably stubborn. If rays come from infinity, they simply seem to diverge from the focus. But if you place an object literally anywhere else in front of a concave lens, it does the exact same thing every single time. It produces an image that is virtual, erect, which just means it stands upright, and diminished, meaning it shrinks. Plus, that image is always going to form on the same side as the object itself. Simple as that.
Finally, Part 5, Lens Formulas and Power. This is the math behind the magic.
So the crucial point is that while visual blueprints are great and all, for true precision, we really need cold, hard math. Here is our master key, the lens formula. 1 over f equals 1 over v minus 1 over u. In this master equation, u represents the object's distance from the lens, v is the image's distance, and f is the focal length. By locking these three specific variables together, we can mathematically calculate the exact optical behavior of any spherical lens. Alongside distance, we obviously need to calculate magnification too, which is just the ratio of the height of the image to the height of the object. But here's the cool part. The numbers actually tell a deeper story just through their signs. If you run the math and your magnification is a negative number, that instantly tells you the resulting image is real and inverted, so upside down. On the flip side, if your magnification comes out as a positive number, you know immediately without even looking that you're dealing with a virtual erect image standing right side up.
Building on everything we've just covered, we finally hit the climax here, the power of a lens, represented by the letter P. Power is essentially the quantified ability of a lens to bend light rays, and we measure it in a unit called diopters. If you wear glasses, this is literally exactly what your prescription numbers mean. A positive diopter means you have convex lenses converging the light, while a negative diopter means you're wearing concave lenses diverging it. Mathematically, it's beautifully simple. It's just the reciprocal of the focal length, 1 divided by f, with the one strict rule that your focal length absolutely must be measured in meters.
So, we've seen how simple particle density forces light to change its path, and how we can use perfectly shaped glass to mathematically bend those rays to our exact specifications. But I want to leave you with this final provocative thought. If diopters give us the exact mathematical ability to bend the fastest thing in the universe to our will, what are the absolute physical limits of what a lens can help us achieve? How far out into the deep cosmos, or how incredibly small into the microscopic fabric of our world can this simple geometry ultimately reveal? The math is constant, but the boundaries of what we can discover might just be limitless. Thanks for joining me for this explainer, and keep questioning the science around you.